Welcome to the deep dive. Right, our mission today, it's highly focused, really technical. We're doing a deep dive into, well, one of the most critical automated systems on any modern jetliner, the yaw damper.
Absolutely.
And if you, our listener, are maybe, wrestling with ATPL theory, flight controls, stability sections.
And this could be really useful for you.
Exactly.
Yeah.
Consider this your essential preparation guide. We want to go beyond just definitions, really get into the mechanics, make sure you can master it.
That's the plan. Our objective here is synthesis, really. Taking all that complex stuff, the aerodynamics, the system logic, the bits that trip students up sometimes.
Yeah, the tricky parts.
And distill it, make it clear, layered, and absolutely exam-ready knowledge. We'll define the core problem Dutch roll, figure out why it happens, and then break down the, honestly, quite clever system that fixes it.
Okay, so let's dive right in. The big question first. Why does this system even exist? Why can't a massive, multi-million-dollar airliner just, stabilize itself naturally?
Right. It's a fair question.
It boils down to speed and efficiency, doesn't it? That swept wing design seems key.
Precisely. To fly efficiently near the speed of sound, engineers introduced the swept wing. It's great for performance, but, and it's a big but, it fundamentally compromises the aircraft's natural dynamic stability.
Which leads to that characteristic wobble.
Yeah.
That oscillation we call Dutch roll.
Exactly. An oscillation that, if you just let it run its course, isn't just deeply uncomfortable for passengers, it can actually be structurally stressful, potentially even dangerous in extreme cases, though rare.
So our focus today, nailed down. Understanding Dutch roll dynamics and the automated solution. That's the mission for you, our listener, prepping for those exams. Okay, to really get Dutch roll, we have to start with the absolute basics of motion, even if it feels a bit like going back to square one. We're talking about the aircraft's axis.
Yep, fundamental stuff, but crucial. 3 primary axes. You've got the longitudinal axis, that's nose to tail, governing roll.
Rolling left and right.
Then the lateral axis, wingtip to wingtip, that governs pitch, nose up, nose down. And the third one, the normal or vertical axis running straight up and down through the center of gravity. That governs yaw.
Nose left, nose right. And that vertical axis, yaw, that's our main focus for today's problem.
Exactly. Because motion around that axis brings us straight to directional stability.
Okay, directional stability. Can you elaborate on what that actually means in practice?
Yeah.
Especially for these big, fast jets.
Sure. Directional stability, sometimes called weathercock stability, like a weather vane pointing into the wind. It's the aircraft's natural tendency, its passive ability, to resist yawing off course and return to its original heading.
So if a gust hits it side on.
Yeah, if a crosswind gust hits the nose, the vertical stabilizer, that big fin on the tail, feels the side slip. It generates an aerodynamic force, basically acting like a small rudder input, to push the nose back into line with the airflow.
You mentioned an analogy earlier, like steering a bike in wind.
Kind of, yeah. You naturally steer slightly into the wind to keep going straight. The fin does that automatically. Generally, the bigger the fin, the stronger the directional stability. But there's always a but in aerodynamics. Drag. A huge fin means huge drag, especially in the cruise. So designers have to balance stability against efficiency. ####B, the cause of Dutch roll.
And that balancing act leads us right into the Dutch roll problem. You described it as an out-of-phase oscillation. What forces are battling it out here? And what's the critical imbalance we need to know for ATPL exams?
Okay, this is key. Dutch roll happens because of an interplay, a kind of badly timed dance between 2 stability forces, lateral stability and directional stability.
Lateral stability being the tendency to resist rolling, right?
Yeah.
Like wings wanting to return to level, often called the dihedral effect.
Exactly. And directional stability is what we just discussed, resisting yaw. Now, the absolute critical condition, highlight this, underline it for your exam prep Dutch roll, occurs when the aircraft's lateral stability is inherently greater than its directional stability.
Lateral is stronger than directional. Why would designers build them that way? Isn't strong...
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best